Okay, the last video cut out before I actually completed my sentence, but basically I was saying that that first application of BSTEM, which is for the first part of the that assignment, has to do with the bank failure when we don't have any augmentation of the strength of the soil materials. And now we're going to look at the case where we're going to put in some sort of protection to prevent the erosion and the mass wasting or mass failures from occurring. So we go back to the original model. If we look at the input geometry, I'm just using the one that the model as before, and I'm just going to put the geometry back in there that we started with, because here presumably I'm trying to stop the erosion from occurring, so we would start with the same geometry. And so I'm just typing back in the data we had. Got to make sure that you're in the correct cell, or else you get these errors. And I find that usually I like to delete all these other numbers that are in the column, these other rows, because they're auxiliary and I don't want there to be any misinterpretation. So this is the original file. The layers are still in there and everything, but difference we're going to have now, the water table depth and all that, and the height of the stream flow is going to be the same, but differences are going to change this to 216 hours. So you can do everything just all in one shot. You don't have to go and do the calculations of erosion in any kind of a sequence. So here we'll view the bank geometry model, and that's that one right there. If we run the bank macro, we still have all the layer properties in there, so we don't have to change any of that. And of course, if we go in here and we run the bank stability model, we should get a value of 1.2. Yeah. So it's the same as what we had before. Difference is now if we go through those sequences of toe erosion, the stream bank gets steeper, and that can lead to slope failure, or at least we demonstrated that it will lead to slope failure. Here we don't really need to demonstrate that further, because we know that the erosion does lead to failure eventually. What we want to do is go back now and look at some options for bank protection. And with the BSTEM 5.2 model, you can put in bank toe protection and not bank protection itself, or you can put in bank protection, which apparently, according to the results, also provides protection for the toe. So if you choose this one right here, then there will be just toe protection. If you choose this one here, there will be bench and toe protection. The options for the bank protection are given in this table, bank and toe protection, and there's plenty of options for you to add your own data in here. But for instance, a coy fiber would be one in which you'd get a permissible shear stress for the toe of 108 Pascal, which is really large compared to the near zero value that we were working with previously. If you one could put in your own data here instead of choosing one of the other ones, and so let's see what would happen if I were to choose my own data. And let's say I put in a shear strength of 5. Or first, actually, let's go first and we'll show what happens with no protection. We already actually know what happens, but I want to demonstrate that. So with no protection on the toe, if I run the toe erosion model, after 216 hours, you see the giant amount of sediment that is eroded out. Now, I'm not going to save this profile, because I don't want it to keep that profile. I'm going to go back now. I know that I get a lot of toe erosion. I'm going to go back to the option for putting in bank or toe protection. Let's say that I put in for my own data here, and I played around with this a little bit, and if you get down around a additional shear strength or permissible shear of 4 instead of the value that it already had for the toe material. If we run the toe erosion model for this, of course, what does it do? It gives me a number which I don't believe. Wait a moment. Let's go back here. Here's my geometry. Bank and toe protection. I've got my own data in there. Let's see what happens here. Oh, I didn't put a high enough number in there. Okay. Thought I had tried that number before. Let's say that I put in plant cuttings here for the toe protection. Oh, and I know. Possibly it's because I didn't provide any protection for the bank either. Because if I only protect the toe, there is a erodible layer in the bank. There's an erodible silt layer. So if I'm going to protect either one of them, I need to protect the bank as well. So here I've got plant cuttings in there, which actually provides a permissible shear of 17. So let's see what happens when I do that. Alright, nothing. There's no erosion at all. I think the reason why I was getting that result when I had my own data was because I was only doing it for the toe and not for the bank as well. So here I'll put in my own data, but now we're going to, and that value is going to be 4.0. Okay, so it's way below the 17 that would be provided by the plant cuttings. Okay, so with that, if I just have a shear stress of shear strength of 4 Pascal, it is sufficient. I can go back and show what happens when we get down to around 2. Cutoff is probably around 3, at which point there's no erosion. So if I put 2 in there, you can see that there is some erosion of the toe and of the bank as well. So 2 is too small. 2 pascals is too small. 17 is way large. And if you're going to do it, well, just put in plant cuttings or this jute net. Those will provide plenty of protection against the erosion. Some of these other ones, coir fiber, geotextile, at least for this situation, they way overprotect. They're not necessary in order to prevent this erosion. Alright, so that's one way of protecting the bank. The other would be if I don't have any protection on the toe at all, I need to have a very, you might say, very strong roots to overcome the bank failure that would occur. So if we have no protection, there's the erosion that will occur right there. If I run the toe erosion model, I get this number for that. And let's say that I export that. So that's my new bank profile because of no toe protection. Okay. If I look at bank stability for that case, you know, we obviously will have a bank failure. So I'm not going to save this yet because I want to go back and I want to run a case of added cohesion from roots with that eroded toe. So I'm going to have that eroded profile that's eroded just from the shear of the moving water. I'm going to put in a additional shear strength of 10 kilopascals. If we do that and I run the stability model, number's already there. The stability is 1.03, which would be enough if we considered 1.0 to be at the failure point. So if you can find a plant root combination that will provide an additional shear strength of or cohesive strength of 10 kilopascals, that seems to be enough to prevent the failure of the slope, even in the event that you have all that toe erosion. Now if you go into here, there are two models that can be used to determine this value, this 10. Well, we're not going to get 10 probably, but let's go in here and we run the root reinforcement model. And so we have to choose some sort of plant. Let's say if I chose alder as being the plant, you can actually choose a bunch of different plant species and ages and mix them by percent of the population that is present. I mean, calculate the mixture of them based on the percent of the particular population present. So here you'd specify plant age and percent contributing to the assemblage. So let's say that the alder trees are 5 years old and that they cover 100% of the bank. Here we can add another species if we want, in which case this wouldn't be 100%, it'd be something less than that. Or we can click here and say, well, we've got all the plants in there. It's 100% alder. So if we do that, the number is 100. I mean the number that we get for the additional cohesive strength according to the riproot model, which is the model currently used within BSTEM, is 0.52. If you use an earlier model by Wu et al., you get 1.9. But with either one of those, we're not going to have enough shear strength. We get 0.52. And if we run the erosion model, or the bank failure model for that, we get a factor of safety of 0.51. So we do need to have some way of increasing the cohesive strength, the effective cohesive strength of material by using plants, but that is not, at least among the plant combinations that we have, there's not enough strength there. Now, what appears to me is that the root reinforcement model, which is built into the this riproot model, which is built into the BSTEM, seems to give lower estimates of the strength, or that additional cohesive strength, compared to the Wu et al. Model and the Waldron model. And because for some combinations there seems to be about a factor of 10 in the additional shear strength that's given by the roots. And which one is correct, I don't know, but in the assignment you should try to determine what the additional shear strength needs to be. And I already showed you a case where I increase it by 10. Then that leads to sufficient strength to prevent the slope from failing. You might look at some other plant combinations to see if you can get it up to anywhere close to that value of 10. Okay, so I hope that this illustrates the application of the model to the situation where we're trying to gain some protection from vegetation on the stream bank.